Okay, member modification factor. So by the way, what we are doing here is this is the wrong standard. All right, just give me a minute. 1170. There you go, I found it. Okay, so today we're going to start with the new standards, which is called AS1720.1 2020 timber structures design methods. And this week's particularly focusing only in one equations, which is very friendly equations that we're going to take you through in the column design, no, and tension member, no, and there is a bending one. Let me find it, sorry. The bending one is there you go. Close 3.2.1.1. They have a bending equations. MD, the number MD, the symbol MD represent the bending capacity of your timber beam, which has a capacity representation factors. As you know, this is on the steel as well. We have 5 factors. We will going to take you through that one, and you have almost 5K values that you need to go through it. There are 5K values that I'm going to take you through. That in the lectures now I'm going to discuss these 5K values, and there is a bending strength, bending stress, or bending strength, and this is like a section modulus value that I'm going to introduce to you as well. So capacity factors, as header already mentions, and from the standards that you can have it, here you go. The standard has given you the two different table for the capacity factors. It is table 2.1. It has given you the value of capacity factor phi, and there is another table 2.2, that value of capacity factor d1. What is the difference between table 2.1 and table 2.2? Is table 2.1 is give you for the members, right? And our course are only covering for the members. So in our course we are just going to use table 2.1. This table 2.2 is dedicated for the joints, and in our course we are not using it for our joints. So we are just using the timber members, not the timber joints. So we only focusing on the table 2.1. As Heather already mentions, I'm just going through these capacity factors, these parameters one by one. So capacity factor is 5. 5 is just a Greek word, 5. I hope I pronounce it correctly. And in that 5 factors, you have a horizontal lines, which is basically specifying your timber grades. So that timber grades are given here. Now for table 2.1, we have a category 1, category 2, and category 3. There are 3 categories that you need to select. By the way, that's, oh, you can't see. Okay, let's put it this way so you can see it. So there are grades like MGP and all. I will go through those grades and numbering as well. There are 3 categories that you can see here. Now in those categories, basically this category number 1 saying that structure member for houses for which failure would be unlikely to affect the area of greater than 25 millimeter square. So if you are designing the members, the timber members in your house somewhere, which is not a primary members, means if something happened to that members, that timber members or timber beam, and it is break only 5 by 5 millimeters, 5 by, so if you have a bedroom with 5 meter by 5 meters, then this bedroom has affected. Not all the houses is affected through that timber beam that is failed. I hope you understand that. If the timber beam fails, and only 5 meter by 5 meter square area, 25 meter square area will be affected. If you are designing that beam, if you are designing the beam which is going to just affect this 5 meter by 5 meter area, your capacity factors is this one. Is, by the way, this is a penalty. This penalty is applying considering the safety of the users, that if something goes wrong, how many people will going to be break their head, or what going to happen to the people who is living there. So it says that category 1 is a low users, like meaning that okay, you if it is break, it will not going to be have a significant affected, because it's just affecting small portion of your house. Probably someone is not going most of the time on that portion, so you have very sensitive. Only 5% to 10% penalty applied. It's just reduction of your bending capacity, that only that much penalty applied. Now category number 2 is little bit more, that this is a secondary, but you have a primary structure member in the structure other than houses, that you don't designing it for houses, some other structures or element in houses, or you can have it on the houses too, for which the failure would be likely to affect area greater than 25 meters. So if you have, let's say, 3 bedrooms and all 3 of them are gone and people are sitting on that, sleeping on those bedrooms or sitting on those bedrooms, then you will have a catastrophic, in meaning that you have a higher penalties applying here. So if you are designing the timber members that will break and it will be affected by more than 25 meters square of area, then your penalty would be up to 30%, up to 10 to 30%, about 15, 20s and so on, depending on what grade you are using. If you use higher grade, your penalty would be low. Like if you are using the stronger beam, then your penalty would be low. But if you are using the low grades, is low grade meaning it will not have too much capacity, then your penalty would be lower. So you have, I hope you understand category number 2. I hope you understand the category number 1. I hope you understand this horizontal line is basically how strong your beam. And category number 3, if you are timber beam sitting in the hospital, sitting in the fire station, sitting in the police stations, where the service, when there is a disaster happens, and like for example recent earthquake, if there is an earthquake and the timber beams fail in the fire station or SES emergency services, then they can't help to the other peoples, right? In that case, there is a severe penalties meaning that your reduction factor goes up to 40%, as you can see. So this is the category where primary structures, so your beam is a primary member plus your post disaster functions. There are hospitals, police stations, fire stations, on such power plants, all those things are sitting on this category. So I hope you understand how you're going to calculate these capacity reduction factors. If it is given in the example saying that this is a primary member of the structures, and if it is broken, then you use this one. If no one given, probably I would suggest to go for category number 2, right? Because category number 3 is overkilling. If someone say that okay, your timber beam is in the hospital, then you go for it. But if nothing written and it's just an office building or houses or something like that, and they not specifically mentions whether it's 25 meters square or not, I encourage you to use category number 2. This is a more kind of a general category. Okay, so you are in between. So more generally, we are going for category number 2. Okay, so that's, I hope you understand that. Any questions there on those reduction factors? Any examples thrown to you in the bending timber beam? Regardless of your category or all, every student should be able to extract the 5 factors. Unmute yourself if you think, I don't know how I'm going to get the 5 factors. You explain me, but I did not understand any single things, or any category that you don't understand. Tell me. Unmute yourself now and tell me that move. All right, so where are we? Here. Okay, so everyone in the class should be able to extract the 5 factors. Okay, don't tell me, okay, I will just tell me more specific details, or this example does not tell me these details. If it's not, you use your design engineering skills, structural engineering skills, you can get the 5 factors somehow, okay, from that tables. Don't stop yourself if something is missing in the example. Just assume and move forward. So that 5 factors is capacity factors, clearly reason close 2.3. All right, so now let's move on to the K1, and that is also in our lecture notes. Let's follow the lecture notes. Now, modification factors, that are 5 modification factors given in our examples. They are dimensionless, meaning that they don't have any units. K1, K4, K6, K9 and K12, there are modification factors and they don't have any unit. They don't millimeter, they don't have newtons, or they don't have meters. So that's the first thing. Good. Model response of the timbers are various conditions. So it's depending on those K5. There are 5 K factors that are depending on your different situations. Like your timber beam is coming into the rain, it is sitting inside the room, it is sitting on the outside of the building, it is in the high temperature zone, it is in low temperature zone, and so on. So it is recognizing the different situations that your beam going to come across during the life of their structure. So that's 5 different categories or 5 different environmental conditions will come onto that timber member that will be recognized by, that would be considered by those 5 factors. Now change the capacity of member in response to the environmental and design conditions. As I mentioned, we are going to take into account the different situations that your timber beam will come across, worst case scenario. There are 5 factors. The first factor's name is K1, which is called duration of the load, that how long the timber beam will going to come across any particular loading, like dead load, live load, wind load, that you're going to consider in your design, how long it will comes onto your beams. Like dead load, they will be there for life of the beam, but live load may not come for the whole life of the beams, right? You may go on the vacation for 1 month, or you may, because of the pandemic, you are not traveling, but you might go to visit your auntie during the Christmas. Your home is empty. What going to happen? That your live load is reduced significantly. So you don't need to design it. That is something that is not. And then sometimes you might say, oh, how do I know? The standards will gonna tell us, right? There is a general trend that we're going to use it. Is a probability, by the way. K1 is not accurate. No one can going to tell K1 is going to be accurate, but we have different case scenarios that we're going to use it, and we're going to consider the critical scenarios. Partial seasoning factors, that if you go and purchase this timber beam, sometimes suppliers will just going to send you the timber beam which is not seasonal, meaning that they are not processed, meaning that they are not be dry in the look. Sometimes these timber beam, they put it in the into the environment for drying conditions, or they sometimes put it in the oven to make it dry. Sometimes they comes in the, if you go in the burnings and if you purchase some of those timbers members, sometimes they comes in the very wet positions, like they have very high moisture content. So standards wants you to recognize whether your timber beam that you are using, in what conditions, what is the moisture content, what is the, how much water that is inside the timber beam, and standard will gonna tell us what would be happens if your timber beam will have a high moisture content, if you have low moisture content, or is a dry timber, what K4 factors that you're going to take. K6, like in Australia, we have a high temperature zones. Like we have a temperature zones in Australia. If you go to the Darwin, top of the north of the Australia, then your temperature is significantly higher. If you go on the Queensland, there is no winters. Like in Melbourne, you have a, like in Bendigo, Melbourne, you have a 0 degree, 1 degree early mornings in the July or in the winter. So you're designing timber member in that Melbourne regions where you have a 6 months of winter, significantly low temperature under 20, and you go to the Queenslands that temperature never falls below 15 or below 20. So in that case, different situations. And in the Darwin, most of the time you have 30 degrees Celsius. So what would be the effect on your timber beam? What, whether strength is going up or strength is going down, whether the timber beam sitting in Melbourne or Darwin. So that will going to tell us. K7s, I think K7s, no, we don't have K7, sorry. There was no K7s, probably this is from the old standards. There was no K7s here, by the way. So K1, K4, K6, K9, and K12. So just don't worry about K7. K9, strength sharing factors, bending strength and bending members only. So K9 is meaning that if you are having the beam which is sitting next to another beam, or when your load applied, how many beams are going to come and carry that load. So is the load going to be shared between two timber beam, load going to share between 3 timber beam, or load going to share between 10 timber beam? Based on that situations, you have K9. K11, size effect. No, we don't have size, sorry. K9, K11 gone. There is no K11, K1, K4, K6, K9. 1, 2, 3, 4, and 5. Last one, stability factors. Do you remember? But that the beam was kicking it out. K12 was when you have a beam, you have a lateral torsal buckling. If you remember, if you don't have lateral restraint, you have take the examples where you have calculate number of FB11, FBFF. There are some F11. That how many beams do you need to making sure that your beam will not going to laterally buckle, like laterally torsal buckle, meaning it will not kicking it out. So here it will happens again. K12, that if you have a beam that is large, and I don't have a ruler. No, I don't have a ruler here. Otherwise, I will show it to you. Oh, here you go. Sorry, that is good. So if you have a beam and if you don't put the lateral rust, then it does this. Right, it will just laterally torsally buckles. The timber beam will do the same. If I put the lateral rust in here, then this beam will not going to have this lateral torsional buckling. It's like kicking it out from their original position. It's very flexible, so you can see. And standard don't like this one. You don't want to design the steel beams like this happening like this. They want you to hold here. So if you does this one, they will not going to kick it out. They will hold it here. So that's the situation that we just want to put it there. So I hope you understand those 5 factors now. Let me go through them one by one. Now, I already show it to you here, this bending, and they say that your bending capacity should be more than m star. 5 MB is more than this one. And they take into account MB straight away here, 5 factors. And by the way, this M star is your design action. So if you have a steel beam, sorry, timber beam, I think I'm just need to focus on that timber beam, and you have W, and let's say length of your timber beam is L. Still, this SD1, they don't depend on your this design action does not depend on the whether you have timber beam or whether you have steel beam, right? If you go on SD1, and then when you calculate the bending moment, it will not going to tell you whether you are designing the steel beam. No, this is independent of the material. So here you still have WL square over 8, meaning that your W length over 8, that is the moment M star. This is your M star value, right? That is your design bending moment or moment demand. You can say that this is the design actions. You can say there are 3-4 names that you can put M star. And again, M star don't depend on whether you are have a team. When the loads comes, what does it mean by it not don't depend? When someone coming on your house, he doesn't know or she doesn't know that you have a timber beam or steel beam, right? They will just apply the load. When the loads comes onto the structures, the load does not know that you have a timber beam or steel beams, right? So WL square over 8 M star value is independent of whether you have steel beam or you have a concrete beam, steel beam, or you have timber beam. You use the SkyShield software. I think in the exams you use SkyShield software. You have a timber beam, steel beams. You have this loading, this one. It does not tell you that prove the Young modulus of this one. It does not tell you. It just tell you what the load and what's the length. So WL square over 8 M star. That is the typical simply supported beam. UDL load and span L. UDL load W. The maximum moment come at the midpoint, and that is WL square over 8. So M star, no one has an issue, and we don't teach in these subjects to calculate M star, right? This is gone way back in the SD1. We don't teach how you're going to calculate M star. We give you the software, and you either we give you the value or you can find it out using the software. So M star, we don't teach you that. So M star is the design bending moment coming from bending moment diagram. So now first one, duration of the load. Now, continuous load at high stress level stretches the wood fiber and breaks the microfiber bond and not record loss of strength over the time. So what happens here? So when you load the beam for significant long period of the time, the fibers inside the timber beams are broke. Broke means there are fibers and you can't see them. When they stretch it out, when you load it continuously, it will be broken in a way that it will non-recoverable. They will not be joined again. So in that case, your bending strength will reduce over the time. The long duration, permanent, and some imposed action cause the reduction in the strength of timber beam. That's what I meant, that you have a dead load that is coming onto the timber beam that you can't avoid. They are there for longer period of the time, constant load over the time. So that is called creep. If you heard about the word creep meaning that when the load is constant, like a permanent load, when the load is constant over the duration, you will have a deflections. That is called creep of the member. So you will have a creep for the longer period, and creep is not good. Creep is very bad. For examples, I will give you an example that before, not long ago, I think you also experienced that one. Coles and Woolworths, they used to give the plastic bags. We need to carry our own plastic bags these days, the recycle one, or you have a bag. we used to have those plastic bags. When you purchase these big like milk 2 liter bottles, then they put it in the two plastic bags, not in the one plastic, so that that persons who is serving you, they know that there is a creep going to occur, right? They will give you two plastic bags to put it on that one, because if you carry the one plastic bags while you're walking from the Woolworth counter to the car park, which is your durations probably 5 minutes, and you have a constant load, which is the milk inside that plastic bag, you might have a chance to tearing it out that plastic bags halfway through from the Woolworths counter to the car park. You may experience this one yeah, in some situation. So the persons who is serving you, they know that you will have a creep problems, so that for that case they generally have this creep situation. So this creeps occurs in the timber beam as well, that if you have a permanent load over the longer period, it will deflect, so you need to take into account that each load combination takes separately for K1 duration of shortest component of each over the life of determined K1, different K1 for members and connections. We are not taking into connections, but I will show you in the standards when we take an examples for the K1. But I hope you understand what is K1. It is just about the timing, how long it will, so that tables will come. I will show you in the examples when we have more on the examples. Now, so K1 is done. So load combinations 1.2 G plus 1.5 Q. Shortest duration of the load combination is crowd. Medium term duration. Generally speaking, this is a general terms that we have these 5 kilonewtons, that will be 5 days will be the general terms. If someone say that what would be the how long your timber beam will be, 5 days. That is the typically we're going to consider medium term, and in that case the K1 is 0. It is in between. It is not worse. It is not over. Okay, it's not under. So K1 typically 0.94. 6% penalty is applied to your timber beam because your timber will experience this kind of long-term durations. And load combinations with wind load, you have only 3 seconds, because the wind load, you don't have a beam where your wind load will be staying there more than 3 seconds, right? Wind generally come and go. So for that case, the standard just wants you to design it K1 equal to 1, because the wind does not affect that much like your dead load and permanent load. K4, which is the partial significators, as I mentioned, how much water is sitting inside the timber beam is recognized by K4. So the strength of the timber is a function of its in-service moisture content. Moisture content is how much water is inside that timber beam, and that is called moisture content, and that is represented by MC. That is the abbreviated word MC that is sitting here. If the moisture content is less than 15, then you just take it K4 equal to 1. You never have a timber beam with the 0 moisture content. So standard knows that you will have a timber with some kind of moisture content. So standard said 15% is okay. We allow you to have a moisture content of 15%. But in case if you are putting your timber beam in the wet environment, let's say your timber beam in Queensland, we have a heavy rainfalls in the Queensland around the year. So your timber beam, have you experienced that your door, your timber door sometimes jam, right? Sometimes you have very hard time to pull the timber door and close timber doors during the rainy seasons. You have experienced that. The timbers absorb the water during the lifestyles. You can't stop them. If you want, even your door is painted, still it happens. You can't stop them. That is a natural process that water comes and goes inside the timber beam over the life of that timber, over the life of the structures. You can't stop them. If you paint it, still you can't stop them. And timber beam drying it out as well over the period that you have a summer, then the timber will dry it out. So timber will become partially seasons, then you take the K4 less than 1. So that's what they say, that if you have lots of water in the timber beam, no good. Standard don't like it that you are putting the timber beam in the water, right? If you have a more rain, if you saying that your timber beam going to experience absorb a lot of water during their service lives, you might need to go for up to 0.7, which is quite significant penalty. 30% penalty, 30% capacity is gone due to that you are not protecting your timber beam. But sometimes you can't avoid it, so you need to have a K4 value. So it's depending on moisture content. Sometimes the supplier, when you purchase your timber beam, they will tell you what is the moisture content when you are going to put it in the service, right? They will tell you what is the how they are supplying it. They will not going to give you the timber beam which is just to soak it in the water, right? Soak it in the water meaning they will not going to send you this timber beam, very bad, right? So they will, when you purchase it, you can ask them what is the moisture content of your timber beam, and it will not be significantly increased over the life if you are not designing in that one. So unseasoned timbers, unseasoned meaning someone will just going to send you the timber beam cutting from the trees and straight away send it to you. They will have a high moisture content. You can see moisture content greater than 25. It has not been drying out before sending to you, and you're going to start using straight away in your timber in your structures. You will have those high moisture content in that one. This is the equations. Though there is another term called, I think, equilibrium moisture content. I think that's what, yeah, equilibrium moisture content, because over the time you will comes to the reach the equilibrium of the situation. Equilibrium meaning that your moisture inside the timber beam and in the environment is almost same. So you are not having too much transfer and too much transfer between the environment and timber beam. Once the timber reach the equilibrium moisture content, then you will have. So they have given you this chart. And this clause also give you these equations based on these charts, where you have a seasoned timber, unseasoned timber, and there is a humidity. Based in these temperatures, you can calculate this equilibrium. So if you know your temperature, you know what is the humidity in your environment, you can find the equilibrium EMC, and you plug that EMC here and you know the K4. So that's how you can use, because humidity, you know what environments like in Melbourne or Queensland, what is the humidity, general humidity you have in the air. You know what is the typical temperatures you're going to design. Based on that one, you can find the equilibrium moisture content from this graph, and from that graph you can calculate the K4 value. All right, so K4 we know this is the tables based on the dimensions of your timber beam. You can select the K4. We will experience this one in our examples. Now K6 is a quite simple. Is a temperature. There are only two values. Either you can take one, or you can have a penalty of 10% K6 and K1. Most of the Australia that you have timber beam here in the white zone, you have K6 equal to 1. If you are in the Western Australia, if you are in the Alice Springs, you are in Adelaide, you are in Melbourne, you are in here Sydney, your K6 equal to 9. Only the regions that are in the gray colors, like in the northeast corner here in this zone of Australia, they will encourage you to take K6 equal to 9, where you have high temperatures, like temperature factors that we call. Here as well you have a K6. There is a 16 degrees south. I think you know the bearing. I think there is a bearing like north and south, and then if you take the line here, and that is 15 degree. I'm not sure whether this line, so 16 degree here. I think this side or this side. I need to check that bearing. So it's just they will tell you this location 16 degrees and so on. So that's the zone that you can design, where you take the K6 equal to 9. Is basically saying that if you are in the high temperature, your capacity will be lower. You are taking this moistures out. It will be humid, hot and humid. It's not only hot, it's about this humidity, right? That you have a high water content in the air that will going to taken by the by the um, taken by the timber beam. So industrial application with high temperature refer special tax for case 6 less than 1. Even you can go more than less than 0.9 for special cases. K9, I think K9 require a lot of little bit details. That, as I mentioned, your beam is sitting into the load is coming onto the one beam, load is coming onto the two beam, load is coming onto the three beams, or is a two beams sitting together. Based on that situations, you have a strand sharing factors. They have equations that's we're going to go through it, and G31, G32, G31, and S and L I will explain you in the examples. Yeah, so number of fasteners element together, that is called N common, and this is N members that I will going to explain you. That if you have isolated beam, you have only one. If you have a closed beam with flexible cladding, you will have a NM equal to 3, NM equal to 5. Closely beam with stiff closing members, I can just show you that one. Let me go back here. Oh, here you go. You have this, you can see N common equal to 4, because you have 1, 2, 3, and 4 beams sitting together, right? And you have only one member, so that is 1, and it is the combined parallel system. You have discrete parallel systems, you have only one beam, and with a spacing of S, then you have a only N combined number of combined beam is 1. This is a, let's say, combined beam, number of combined beam is equal to 4. You have stick together. There are only and you have how many members? You have 4 members. How many number of members? You have 4. You have this combined and discrete system where you have a combined number of beam is 3. You have a number of beam is 4. Then you have this one, and there is a table here that we're going to use it to calculate G13 and G32. So that's we're going to and then once you have that one, you can plug the value, which is your S is the spacing between the beam, and if you take the span of the beam, that is the length of the beam, that is L. And G31 and G32 is just read from the tables based on your N combinations and N combination and N numbers. All right, so that's what they talk about K9. That let's say you want to calculate the K9 for these members, that you have a system with parallel main members bridging all these K9 is appropriate. So common is number of combination equal to 1, because you have these situations, you have only N common combination equal to 1. And you have a number of member 3, because when you apply the load, they will share between these two members. So there is 3 members that will be flexible, this one, and then you will have G31 and G3 just coming from here, that you have a N combination 1, and 1 times 3 you have this, so 120 and 1, that's what they return. So because your N combined factor is 1, number of member is 3, 1 times 3 is 3, so you have 120, and your N common is this one. So you have G31 is 1, G32 is 1.20, and you plug the value here. You plug the value here to get the K9. So you just plug the value here. Spacing is 450, and span is 300. So span is meaning that they are just doing this span, right? This length is 3500. So that's the span. K12, last one, as I mentioned, the beam will going to kick it out. You know, the beam will have these lateral torsional bucklings. In that lateral torsional bucklings, you have a K12 factors, and we need to calculate these rho B and S1. If it is less than 10, we will have K12. If it is between 10 and 20, you have these equations. If it is greater than 20, you have these equations, and I will tell you how to calculate rho B and S1 in our examples. So timber member under the bending, you have generally rafters, purlins, lintels, wall stud, barriers, and joists. I think they have a figures at the start. where they have definition of all these on here. You go. This is lintel. You can see there's above the frame of the window and door and all. You have this lintel to support your frame. You have a rafters on the roof. You have these horizontal members that are called rafters. This is the on the roof. You have a ridge beam. So those are the typical timber members. You have barrels, that also the timber members. You have these joists, that's also the timber members. So those are the some of the typical vocabulary that we use in the timber. So that's all the listed here, but those figures will helpful if you like to go back and read them and just you don't need to remember them. It's just many members have primary compression and tension member also have a bending action, so you need to have a design it for. So we will talk about this compression and tension next week probably, those compression members, and we need to do it for both. We need to do the strength check and serviceability checks, and for larger bending moments you need to have a glue lamp and LVL. So generally we have MGP grade and F grade, but in case your M star value is greater than your capacity, then you need to go through this glue lamp and LVL grade. So Australia has those glue lamp and LVL grade available in the market, so that you can use it if your bending strengths, if you don't have a set cross sections and everything you try and nothing works, then you can use the glue lamp and LVL grades. I think we discussed this one all. Let's take an examples now, and probably most of the things that we're going to talk about that we'll also going to revise, and I will take you through. All right, let's move on. One equations, very friendly equations, 5K values, and we are on our way. No any big issues here. So let's continue. I think for the answering the students' questions, I need to get the one kind of where is it? Oh, here you go. Let me prepare it so I will not get lost. Oh, there you go. All right, let's start now. And we go through it. Find the fluxures. Find the fluxure strength of 140 by 45 MgP12. So we have given timber sections, which is MgP12. By the way, MgP is the grade, and 12 is, I will tell you what is the meaning of 12. And this one has a 140 depth, 140 millimeter depth, and it has 45 width. 45 millimeter width. So let's talk B equal to 45 millimeters, D equal to 140 millimeters, that is given. Now MgP12, now standards has given us some tables. So if you go on the appendix, here you go, in table number #3.1, you have a different kind of grade. MgP12 in the markets, if you want to order, you order like this. I want one MgP10 70 by 35. I want MgP10 190 by 35. That's how you order it. Okay, these are the standard size available in Australian market. MgP10, MgP12, and MgP15. Now what is MGP? I think I'm not sure what is the full name of MGP. I need to dig into that one, but this is the grade name MGP. If you go in the bondings, even you can read that MGP grades as well. So this MGP, and these are the size. Now what is 10? Now 10 is referencing to the, let me tell you something. There was a called elastic modulus. Where is it? Yeah, here you go. This one MGP10 referring this Young modulus, how stiff your timber is. That is 10. You know the Young modulus, like stress over strain, right? That is in the elastic region. So 10 meaning you have a 10 stiff. MGP12 is referring your threshold value of your stiffness. right? You ordering this one, you are ordering more stiff for value. By the way, if you are, I can explain you that. So if you test the timber beam under tension, and if you just put the stress or strain, like if you have a timber and you just pull it and you draw this line, elastic one, then you know how much load you are applying, right? Let's say this is the timber that you are applying. So this load over area will give you the stress. That will give you the stress. You can record it, the value, and how much it's going to extend it. Let's say you have original length is this one. After testing, it will be extended by, let's say, length plus delta L. So this is a change in length. Change in length over original length, it will give you strain. So you can plot it here. Then you just take this stress value from here to here, and you take the strain value here to here. You can get the Young modulus stress over strain, the difference. Let's say this is sigma 2, this is sigma 1, sigma 2 take away sigma 1, respectively strain take away this one. So you can take the slope. Now if you this is, let's say, mgp 10, that is just a 10,000 megapascals as a Young modulus. Now if I want to increase the, if I test mgp 12, I will get this slope, right? That is mgp 12, right? There is, let's say, 12700 megapascals, that your slope is increasing. So for that case, if I apply the load on the beams, you can see this will deflect less. It will just going to get that deflection. This will get more deflection. That's what if you use higher Young modulus for the same loading, you will get less deflection, so more stronger. So that's what this is numbers representing mgp 10 and 12. So that's basically here mgp 10, 12, and you can't just go more than that. Mgp 15. I have, by the way, the timber. I'm not sure what grade you have. mgp, I can see mgp 10A. Can you read it, right? You can see mgp 10A. I'm not sure what is the size. So it's mgp 10, right? mgp 10. Softwood framing has 12. Yeah, mgp 12. And what is the size? If you want, size is, I can put it here. The size is about depth is about between days mgp 12 between 70 to 140, about 85, yes, here. And the width is about 35, yes, 35. So that's quite reasonable. mgp 10 and this one, you have seen this kind of timbers, right? In Australia, we have this kind of cross section. So that is the mgp 10, and this is all the properties that I hope you understand these 10, 12, and 15 configurations. All right, continue. So where we just finished first line, and that would be season floor joists. Okay, that is seasons, good. So that would be, let's put the more details there. We have B equal to 45 millimeters, D equal to 140 millimeters, and then you have a season timber that is given in this one. If it's not given in the example, you can assume season or unseason. Generally assume the season. Floor joist, like a floor joists, meaning that you have these, let's say you have upstairs, so you have these floor joists here. For an office in Adelaide, so you have it office building. So you have a office building, and it is part of it is in the city Adelaide. Okay. All right. Then what else? Strength limit state load combination. So we need to do the strength limit state. It is already factored imposed action. So factors meaning it's already 1.2 G. They already multiply for us. So that is, please pay attention for factor load. So 1.2 G, dead load 2.04. So 1.2 G, 2.04 kilonewton per meter. It's already factored. It's already included. And then you have factor permanent I think this is G, permanent one is 1.2, G is 0.4, and the live load is 2.04 kilonewton per meters. Okay. All right. Uniformly distributed load simply supported designs part 2.65. So from here to here, that is 2.65. That is 2.65 meters. That is given here. I think from here, that is 2.65 meters. And that is uniformly distributed load and simply supported. So like this, and you have 2.65 meters and uniformly distributed load that is given to us. Then floor is 24 millimeters, F11 plywood, nail at 300 millimeters end. Flooring is 24 millimeters, F11 plywood, nail at 300 millimeter centers. We will get back to you that spacing between the floor joint is 450. So if I take it this one, so from here one to another one is 450 millimeters, right? So that's given to us. All right, now let's move on. That we have an equation here. That equation is this one. We're going to use MD equal to MD greater than or equal to M star. So we have supposed to be MD capacity should be greater than M star, right? And that is coming from the clause 3.2.1.1. Now M star, let's get the M star, which is denoted as a design bending moment. That is coming from your bending moment diagrams. Now let me go through that bending moment diagram. So we have, if you have a uniformly distributed load given to us, less designated by W, and length L is 2.65 meters given to us. Then the W that we just want to calculate is let's say the W would be 1.2 G plus 1.5 Q, and that is given to us is 0.4 and 2.04. So 0.4 plus 2.04. In that case, you have, look at the dead load is very light because it's a timber. Live load office building, so you have more live load, 2.44 kilonewton per meter. So that is your D. So if I draw the bending moment diagram, there is a parabola for uniformly distributed load, and as I mentioned, this bending moment does not recognize whether you have a timber beam or steel beam. So you have W, which is 2.44 kilonewton per meters, times by length is 2.65 square, let's say meter square, over length is 8. So the M star would be 244 times by 2.65 square over 8. You get 2.14 kilonewton meters. So that is the M star. M star equal to 2.14 kilonewton meters, right? That is the first thing that we calculated. So our beam, which is 145 by 45, should have a capacity more than 2.41, 2.14. So our capacity MD should be greater than 2.14 kilonewton per meters, right? Otherwise, we need to redesign the beam. That is the strength, bending strength check. Now let's continue doing that examples like MD. Let me copy that. Equations. MD equal to 5 K1, K4, K6, K9, K12, FB dash Z. Okay, that's fine. So 5 K1, K4, K6, K9, K12, FB dash Z. Right. Okay. So if I ignore everything and I take you all the way to mechanics of solid, year 1, semester 2. So you have known the bending equations, bending stress. This is called bending stress bending stress equal to my over I. Right? This is the equations to calculate a bending stress. What does it mean? So if you have a beam and if you bend it, let's say if you have a beam and you bend it, if you bend it, then you have a bending stress like this. The bending stress here, let's say you bend it with the moment m, distance is y, where you want to find the bending moment. I is the moment of inertia, y is the distance from the neutral axis where you want to bend it. Then you can calculate the bending stress is equal to my over I. How much bending stress? So this is, let's say, bending stress sigma b. For example, if I have not a timber beam, but let's say I have this beam, and if I bend it like this, what would be the bending stress that will be appearing here, which is the bending moment, how much moment I am applying, I need the moment at that much, distance y, that from the neutral axis, because you have a specific zone where your compression and tensions are separating, because above this line your materials are squashing, below the line materials are extending. In that case you have a bending stress. Bending stress is equal to moment that I am applying, distance y from the neutral axis where you want to calculate the bending stress, because that's the point where you're going to experience the largest bending stress. And I is just BD cubed over 12, moment of inertia, the resistance of the beam due to the geometry of the beam, right? That is BD cubed over 12. So that's is known to you. That's fundamentals. Every engineer should know that bending stress is my over I. So as you know the standards, now in here the Australian standard says that this is FB. This is the just name, that it is just FB. Okay. So standards is just saying that this is your FB. That is fine for me. That's okay. This they talk it MB. MD. That's fine. So I can just rewrite that FB equal to MD Y on I. That's fine. Okay. Oh, sorry, MD. MD on Y. That is just a different notation, but the same equations. Okay. Now, what happens to the I and Y? So FB equal to MD equal to just I over Y. That is your section modulus Z. Z is equal to I over Y. Meaning that FB equal to MD on Z. Meaning that if I want to calculate a moment, which is FD times Z. Oh, sounds good. FB times Z, right? That's what it happens. And in between, you just throw some of those non-dimensional factors. So these equations that standards giving you is nothing but your mechanics of solid, right? So let me calculate that quickly. FB, that we're going to get it from MGP12, by the way, and table has 3.1. Table has 3.1, MGP12, right? MGP12, and what was the cross sections? MGP12 and 140 by 45. MGP12 depth is 140 and 45. So 140, your bending strength is 28. Everyone agree? That MGP12, this does not matter which width you are using. You have a 140, and for 140 your bending strength is 20. FB dash is 28. So that sounds good. Let's plug that 28 here. So you have 28 megapascals, and the Z is, by the way, is BD square on 6. How this I coming from? Let's say Z is equal to I on Y. I is BD cubed on 12, and the Y is D by 2, because basically you want to find this D by 2, right? Because this is the whole D. So in that case, you can just have a BD cubed over 12 times by 2 times D. So this one cancels, BD square on 6, right? So this is BD square on 6. Z value, let's calculate separately. This is FB dash, and that is coming from table H 3.1, Z value BD square on 6, D is 45 because I think we take the notes of that one. B is 45, D is 140. D is 140 square on 6. So you have 45 times 140 square, 40 square divided by 6. You get 147000 millimeter square. So MD equal to 28 megapascals and 147000 millimeter square. And by the megapascals, you can write Newton per millimeter square. So 28 times 14700. So that will have a 4116,000 Newton millimeters. And then you just divide by 1000 and divide by 1000 to get it into, so 4.11 kilonewton meters. So look, if you don't know timber anything, and if you are sitting in the with the architectures and you want to do the quick calculations within 1 minute, you can tell that your m star value, which is 2.14 is your MD value is your MD value, which is 4.11. It is conservative, less greater than m star. I'm okay. I'm okay, meaning my value will not be significantly affected, right? If it is reduction by 50%, how much I'm away from? How much away from, meaning 2.14 over 4.1111. How much extra capacity I got? 4.11. I got about 52% capacity extra. If I get the penalty up to 52%, I'm reaching close, right? But I'm safe. 52% penalty is quite heavy. So if I come across with those 5 factors and capacity factors, I still be safe side if I not reach 52% penalty. So if you do the timber examples in the exam and someone said, oh, it's quite hard. No, it's not hard. If you don't know your 5 and K1 to K5, still you can tell your engineers whether it's going to work or not. Of course, it's not full, but at least you have a pictures. Within less than 1 minute, you are in the position to tell by looking the beam whether you're going to be fail or not. Of course, as I mentioned, it's conservative. You don't take into account K1, K4, K9, K12, but at least you have a clear pictures. At least you know that beam going to work. Okay, so that is just a quick overview. Some of these details we're going to use it. So let's do the real one now. That real one is MD. Still your M star is still the same, 2.14 kilonewton meters. So MD capacity factors K1, K4, K6, K9, K12, FD-Z. Now capacity factor 5. Let's go back to the table number. All right. Table number 2.1. Don't use table 2.2. It's a joint. Table 2.1 is the member. We have different categories. Category number 1, category number 2, and the category number 3. As I mentioned, MGP 12, stress grade, MGP 10, this one, and higher F grade, all other timber and stress grade. So we are false in this category because we have other timbers. We don't have MGP 12. We don't have this one. So we are in this line. All others are not. So we are either this one, either these ones. Let me check. So I'm going in the right directions. Yep. So we have this one. We have this one. We have this one. 0.6. Okay. So we are in these categories. Now, structure member for houses for which failure would be unlikely to affect the area greater than 25 secondary members in structure other than the houses. So we look like we have a joist which are not a primary members, like I can show you in our examples. We look, this is a primary member. Look, this one is a primary member. If this one fail, it will take all these parts together. You understand what I mean? That if this primary member is going to fail. If this one fail, meaning that this will fail, because this will come down, this all going to come down. So this is not a situation. You have 5 by 5 more than this one. Now if this one come down, it will just come down to this only part of this one. So you happy with me that to go for this category number 1, which is not greater than 25 meter square and secondary members. For that case, you happy with me, penalty 10% to be taken, 0.9. Do you agree with me? Well, someone said, oh, I don't agree with you. People is a kind of primary members. If it is hit and is sensitive, then you have a 30% penalty. Okay, this 0.70. You might upgrade this one. You might need to come back and revise it. But I'm happy with 0.9 because it's not a primary members for me. So 0.9 table 2.1 category number 1 and MGP 12. Okay, so that's the information that we needed. Okay, K1, that is the questions that students has asked, and I need to provide more information. All right, K1. Okay, when you construct your members, your loading are very small. First day, you take a occupancy. You will not have, you have about this 1 to 1.2 to 1.4 kilonewtons of loading. Significant period, you have vacations, you don't invite a lot of guests, you have some vacant positions. Take an occupancy, let's say you have family, you getting older, you become grandparents, you have grandkids and all, again some of the occupancies are come here. So overall, if you take the average for whole duration of the period, you might have 50 years of structure's life. During the 50 years, you might end up with the 5 years of 5 days or some stage where you will reach the ultimate point. Ultimate point meaning that you have a 50 gates comes to your house. You might have this one. In the normal situation, you have 2-3 people. That was not we designing. We are designing for ultimate situation. In that case, you may not have these ultimate situations coming into that situation. So the standards will recognize that. This is the tables that we're going to use it. That you have only dead load 1.35 G. By the way, I need to show you that what I'm talking about. So here you have two options. You can use table 2.3 and you have this K1 value given to you. But the problem is you have 5 seconds, you have 5 minutes, you have 5 hours, you have 5 days, you have 5 months, and you have 50 plus years. Now these values, depending on how your structure is sensitive. Sensitive means how much your load will going to come on to the structures. Now these tables does not help, because if you have 5 seconds, you no need to reduce it. If you have 5 minutes, no need to reduce it. But 5 hours and more, your capacity is reduced, and sometimes you will get the significant penalty about 33%. You can't go for 33% penalty, right? It's quite severe. In case you want to design something which is whole 50 years, your structures will be getting that ultimate load. Now it still does not help me. So in that case, you need to go to Appendix G. Now in the Appendix G, you have various load cases. Like here they have mentioned here. For strength limit, the critical strength limit load combination may not be the one that is the highest value because of resistance of timber to the load function duration of the load. In some cases, you have questions there? Involving longer term load, lesser load effect. So what this note saying that, look guys, you need to analyze all of these load cases. You need to do 1.35 G and you do this one. You need to do this live load, and you don't know which load scores would be the critical. So you need to repeat the whole design for this one. You need to repeat the whole design for this one. You need to repeat the whole design for this one. So you need to repeat for this, and you don't know which one going to be acted critically. Not my one is written here on clause 2.4.1. You have written here. So that is the notes that you need to design this. And what is this one? 1.35 G. G, by the way, dead load, and Q, by the way, the live loads. Okay, let me put the lines down so that you understand that. Now, so I hope you have these dead loads, live loads, wind loads, and short-term factors, and you have different. So these figures will help me. These figures going to help me that you have 1.35 G, or you don't have any occupancy. You have just the structure. So 1.35 G, 50 years, and Q not included, only structure self weight. So in that case, just the self weight of the structures. 1.35 G, quite serious. That is 1.35 G, 0.85, 0.57 for this one, quite high penalty. Now, then you have permanent and short load, roof lie load, roof and floor load, and this one, it says that you have dead load and you have live load, some occupancy as well, some short-term factors, and you have 50 years, and again this one. So in that case, you have different load cases, and for those load cases, you have different values given to you here. Now the third one, that load case, is that for 5 days, this is the typical case that you will have a normal short-term imposed load. Strength limit, state magnitude, short limit says you have a dead load and you have five. Look, this is a party at your house. How many times you will throw the party in your house? Something Christmas time, and so on, and so many people. I'm not talking about every corner of your house will be filled by someone in your house. That is the ultimate load that you are talking about. Every corner of your house will be filled by someone. Then you will have 5 days 1.2 G plus 1.5 Q. You have 5 days scenario, and that is here, I think 1.2 and 1.5 G. And similarly, you can think of this wind load. Wind load just come for 5 seconds. So for that case, you just take into account the 5 seconds. And again, I'm not saying that someone is winning. Only you need to check for whole cases. Now, so in our case, that we might have situations where every corner of the office will be filled 1.2 G, 1.5 Q, and that would be filled by someone. In that case, let's say we will have a Q1 value of 0.94, roof live load and distributed, because we have it on the roof side. So we take it 0.95, and by the way, that is for 5 days, as I show you on the table. So that is coming from here, 5 days, 0.94. Someone might say, no, I'm not agree, I want to go for those 5 months and solve, but you are making your expensive. So for our case, 5 days, 0.94, office building, 1.2 G plus 1.5 K. And I'm not saying it is a critical one, but for our courses, and we are not checking for whole these all, but I think you are in the positions to take into account all the cases in the real world for your exams. If you come across with this normal situation, office building and all, we typically do it for 5 days, because it's 1.2 G plus 1.5. Now students ask me the questions. Does it answer your questions there? Okay, that's good. Look, this is a probability K1. This is no one, even I'm not in the positions that your structures would have more than 5. It would happen, but this is just a probability, right? And for that probability, we take into account the 6% penalty, as you can see in the beam. All right. So K4 now. K4 is from the from this close. We have a season timber. We have these season timbers. We have a season timber. So for season timber, generally K4 equal to 1. For season timber is subject to a condition of the average moisture content 12 months period exposed to this exceed 15%. Generally, we have MGP 12 and all these standards when they have a moisture content less than 15%. So we take it K4 equal to 1, because we have given in the examples K4 equal to 1. Close 2.4.23, because we have a season timber, and if it's not given, we assume moisture content moisture content less than 15%. Now, in case someone will send you the moisture content or equilibrium moisture content, if your supplier supply you equilibrium, is very easy to predict. One, take away 0.3, you put the equilibrium moisture content here, take away 15 over 10, you can calculate that, or you can take a 0.7, whatever the minimum highest value of annual average moisture content percentage that timber will attain in the service, right? So you can easy to do. If it is on seasons, you can take it from here, but it is given in the season, so it's K4 equal to 1. K6 K6 we are in Adelaide. As I show you the map, timber under ambient condition, no modification for stand need to be effected temperature K6 equal to 1, except where season timber is used to structure erected in coastal regions of the Queensland. I show you that map north of latitude 25 to the south, and all other region of the Australia north of latitude 16 degrees south tend to be modified by factor K6 equal to 9. We are in Adelaide, is given in our example. So temperature factor K6 equal to 1, and that is in the clause number 2.4.3, and that will have a Adelaide city. So Adelaide is not high temperature zone, and high temperature zone are just Darwin and Queensland. K6 equal to 1. K9, unmute yourself anytime if you don't understand, because we covered this one multiple times, but I just need to show you on the standard. So K9 has these equations that we're going to do it. Close 2.4.5.3 G31 plus G32, take away G31 1 minus 2s on L. Okay, now we're going to calculate each one by one. That we need to get G31 and G32 from this table 2.7, geometric factor for parallel systems. So we will have a combined number of combined beam, and we're going to get a total number of members in parallel systems and combinations times the number of members. Now first of all, let's calculate the n combinations, and if you need, they have given you these figures that if you have this kind of system, this kind of system, this kind of systems. Now by looking at our figures, we look like we have these systems, like a B system, discrete parallel systems. Why? Because you can see you have a beam which are sitting like these beams. You can see there are discrete systems. So in that case, we can note it that we have n com equal to 1. Combination of number of beam n com equal to 1. Now second, n number of members, MEM, by the way. Now in here they did not mention anything, but we can say that when you have typical these kind of structures, you have a load sharing between one on the left side, one on the right side. So we can say that there are three number of members that we're going to do the load sharing. So in that case, we can just calculate n combinations. We have 1, so you have G31 equal to 1, table 2.7. So G31 equal to 1, table 2.7, you need n combination equal to 1. And then you calculate this n combination times by n member, number of member, 1 times 3 equal to 3. So in that case, we have a n combinations times n members, you have 3, you have G32 1.2. So you have G32 1.2. Now spacing is given in our examples. Now, by the way, spacing is given here, that the spacing is the center to center distance from one beam to the next beam, consecutive beam. So that is the spacing. Now that spacing is given in our beam is spacing between the floor joints is 450. Basically from one to another one is a 450, right? Yep, that is 450. So that spacing is given as equal to 450. As equal to 450 millimeters, and the length is given to us. By the way, the length is given to us is 2650. The length is from here to here, which is 2650 millimeters. So length is given 2650 millimeters. 2650 millimeters. Now we are in the positions to calculate all this one. G31 is 1, G32 is 1.2, take away 1 take away 2 times 450 on length is 2650. So in that case, K9 we going to get is 1.13 using the calculators. Now the last one, the buckling one, the lateral dorsal buckling. Now for that buckling one, we have K12. I think the K12 is stability factors. The K12 we call it stability factors, and given in clause 3.2.4. 3.2.4 stability factors, we have to calculate rho B S1 and so on, and then once based on this one we can calculate the stability factor. So this is the stability factors, and that is given in the clause 3.2.4. now we need to get the rho B first. Now rho B is called material constant. If you turn the page over, you have material constant rho B, and we have MGP12. We have just read the material constants 0.85, MGP12 0.85 from table number 3.1, and we have MGP12 grade. So S1, S1, if you just turn the page over, there are different configurations given to calculate the S1. Beam of rectangular cross section. Yes, they have a beam with rectangular cross sections. So for that case, we would beam with the rectangular cross sections. We have a situation like this. We have timber beam. The uniformly distributed load is coming on here, and we have a restraints provided to us in that fashion. So you can see there are restraints LAY given to us. That's that I can point it out. That restraints is given in our questions, that you have a flooring is 24 F11 plywood, nail at 300. So you have a plywood floor on top of this one, and they are nailed at a distance of 300 millimeters. So those plywoods are nailed at 300 F11 plywood. So there, I think they are talking about this F11 plywood, this one, as you can see, and there is another one going. So there is at a distance of 300 millimeters. So if you take it here, so that is given here, that another like you have this beam, and on top of you have this plywood beam sitting on top of it, that are 300 millimeters. So they will provide the restraint about this dorsal buckling. So we have LAY, like here in this timber beam you have LAY of 300. So we can use these equations here. S1 equal to 1.25 dB LAY on D to the 0.5. Okay, so that equation I'm just copying it down. My surface is okay. S1, now you have a 1.25 D on B, LAY on D, 0.5. Now in that case you have to plug those values. 1.25, D is 140 over 45 given in our examples. LAY is 300. I just told you that 140 to the power 0.5. in that case you have a S1 is 5.69. Now you can just multiply rho B to the S1, then you will have a 0.85 times by 5.69. 0.85. So that value you will get 4.5. So 4.5, meaning it's just less than 10, meaning that you will not have a lateral dorsal buckling. So we have K12 equal to 1. So that is there is 4.5, which is less than 10, meaning that K12 equal to 1. Okay, we have everything now to calculate MB value. MB equal to 5 K. Let me get that one. Okay, 5 K1, K4, K6, K9, K12, FB dash and Z. 5 we calculated 5 was remember that category number 1 and all 0.9, 0.94 and 0.9, K1 0.94, K4 value was 1, K6 was 1, K9 we have 1.13, K12 we have 1, FB dash I think we get that FB dash value as well. Remember that before I calculate that 28 and 147,000 Z. 28 megapascals times by 147 millimeter to the power I think cube. All right, so if you just multiply all these values you get 393 48 8136.7 Newton millimeters. So if you just divide it by let me just plug it into my calculators. 0.9 times 0.94 times by 1.13 times by 28 times by 1470. So you have 393,813.7 Newton millimeters. So if you just divide it by 3.9 kilonewton meters, so you can see the value 3.9 kilonewton per meters is greater than your design demand, your M star value, which is your 2.14. Is your 2.14 kilonewton per meter. All right, so you remember that without those penalty we have MD equal to how much? Was very crude and was 4.11, not bad. How much penalty we get? 4.11. So 3.9 divided by 4.1, you get about 5% penalty, because if I just 3.9 over 4.11, you get about 6% penalty that you get it from those factors. So not bad. So you can say that the MGP 12 140 by 45 timber beam is adequate for bending strength. Of course, you need to check it for different load cases, but I hope you understand the scenario. And let me know if you have any questions there.